All right, let's continue this discussion on the connections between centroids and moment of inertia. One thing I want to remind you that an integral is a sum. So here's the equation for the center or the centroid, the x position of the centroid of some arbitrary shape, right? And there's an integral at the top, integral at the bottom. And what you might recall is that if I took consider the CD on here as perhaps the hole or something maybe I drilled into the white surface, or I could just add that on, right? This might have a little more area, but let's pretend that's a hole that's been drilled out. And the way that we do that is we take the centroid of the rectangle and then the centroid of the CD or DVD, whichever this is, and we add them together, or in the case of the CD, we subtract it if it's a hole, right? Because you're taking that away, right? So the integral is a sum. Well, the same thing holds true in here when I look at the rotational inertia. Now, one thing I want to discuss before we get too far, when I talk about the moment of inertia about the x-axis and the moment of inertia about the y-axis, that has to do with rotating it around the x-axis. Whoops, yeah, this would be the x-axis. Okay, let me do it this way, and then the y-axis, which is this way. And I'm holding it very specifically where the y-axis is running through the center, the x-axis is running through the center. So these are the equations that work if I'm talking about the x-axis or the y-axis that goes through the centroid, right? Very important. This works for the moment of inertia about the x-axis or the y-axis passing through the centroid of the shape, or in the case of the mass moment of inertia, through the center of mass of the shape. All right, but again, I have an integral, and so an integral is a sum. And so to keep my life nice and simplistic, I'm going to take this CD and I'm going to place it, so the centroid of the CD and the centroid of the rectangular shape are the same. And so now the moment of inertia of this combination would be the moment of inertia of the rectangle plus, in this case minus if it's a hole, but plus the moment of inertia of the hole, which I guess I'll just say the hole is going to be negative, right, because it's got a negative area. So you're going to add those together. So around the x-axis, this would be the equation, and you do the two integrals. You don't have to do two integrals, all that's been done because these are nice shapes. And then around the y-axis in this direction, you'd have two integrals to do. So if I have a combination of shapes, we're going to add those centroids together. Okay, we're going to add those centroids together. Now, that works all well and good, right? And I said centroids, I apologize. I should have said you're going to add those centers of mass together. No, I'm going to try that one more time. You're going to add those moment of inertias together. But what if I'm not rotating about an axis through the center of mass? So this is going through the center of mass, but what if I choose an axis at the end? My axis of rotation is there, or anywhere else for that matter. Then the problem becomes a little bit trickier to do, and we use what's called the parallel axis theorem. And the parallel axis theorem says if I choose an axis which is not through the centroid, so I'm going to call that x prime. So maybe, let me actually do y prime instead. So here's the y-axis through the centroid. And then maybe I'm going to choose an axis over here. And I'll call that y prime. And parallel axis theorem says that axis has to be parallel to this one. Right? So the two axes have to be parallel. Well, then these two axes are separated by some distance d. Okay? And what the parallel axis theorem says is that the moment of inertia around the y-axis, the y prime axis here, and it's different, right? It's going to feel different if I take this bar and I rotate it about the centroid. That's kind of difficult to rotate, but if I rotate it about an endpoint, it's even more difficult to rotate. So it does matter. So what that says is that this is equal to I sub y, which again, remember, that's the integral of x squared dA. But I add to that d squared times a. So d is the distance remember they're parallel, right? And parallel lines are the same distance forever. So d is the distance between those two parallel lines. And so I'm going to get I sub y plus d squared a. And I don't like the way that's looking because it looks almost like a differential. So let me say ad squared. That way you don't look at that and think that maybe that's a differential area, right? So that's going to be the moment of inertia. Now if I add the hole in there, and maybe I'm going to put the hole over here, right? Then I've got a different distance between the centroid of the hole and that, so I'll call that d sub h for the hole. And so I would need to subtract, because it's got a negative area, the values for that as well. So you might not have all of them have the same distance from that axis. The centroids of them all might not be the same. All right, so we've done problems similar to this when we talked about centroids. And again, I keep saying centroids, I mean moment of inertia. Moment of inertia, I apologize. But the moment of inertia, the problems are very similar to what we did in the past with centroids. And I'll also point out, in the book, you had the position of various shapes, like triangles, rectangles, circles, etc., where they told you where the center of mass or the centroid was located in those tables. Well, the moments of inertia for nice shapes, circles, rings, cylinders, cubes, etc., the moment of inertia and the mass moment of inertia can be found in tables in your textbook as well. So you want to make yourself familiar with those tables and keep them with you. All right? I hope that's helped out a lot. I'll try and get another video up here with an example in it, and we'll go from there. If you have any questions, please leave them in the comments below. Thank you.